When you think about automation systems, what comes to mind? Streamlining industrial processes? Yes. Lots and lots of motors? Absolutely. So, if we want both of those things to happen, we need to make our automation systems smarter and safer. And we need better diagnostics into those many motors. So, how can we do that? Well, there are a lot of different options. But one particularly interesting way is with the use of smart actuators. And folks, you guessed it, that's exactly what we're talking about today. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Louis Gobin, Ryan MetIvier, and Roberto Sannino from STMicroelectronics join me to chat about how sensing and actuation data can be combined in predictive maintenance applications. The benefits that STMicroelectronics' smart actuator development platform can bring to automation systems, and how you can take advantage of this development platform for your next design. And before we get started, don't forget to click that link. There you can find even more information about this topic from ST Microelectronics. Hi, Louis. Thank you so much for joining me.
Thanks, Amelia. Thanks for having me.
Sure. And hi, Ryan. Thank you for joining me.
Hey, Amelia. It's my pleasure to be here today.
Excellent. And hi, Roberto. Thank you for joining me.
Hey, Amelia, thanks for hosting us.
Absolutely. Okay, so Roberto, what are smart actuators? And talk to me about their role in the evolution of automation systems.
Okay, so a smart actuator is first of all an actuator that can be controlled at low level to optimally execute specific actions. For example, in the case of a brushless DC motor, you may typically implement sophisticated algorithms such as field-oriented control that are based on the motor's physical model and that achieve nearly optimal performance in terms of precise control of torque and speed, high efficiency, reducing power losses, and in general, smooth operation. Now, when this smart actuator is within a system, it becomes a more complex machine. It may heat up, it may vibrate. In general, its behavior may be affected by unexpected factors such as load changes or other physical conditions that are external to the motor itself. This means that in this case, you may want to control it based not just on the physical motor model, but also taking into account its operating context. And your algorithms to control it must become smarter. At this point, you have a smart actuator where you can optimize the behavior, making sure that the system always operates at its best operating point, taking into consideration boundary conditions to improve efficiency and lifespan. You may implement diagnostics where the system itself properly identifies what is going wrong whenever something strange happens. And in this case, for example, you don't need to have a maintenance team that investigates what happened because it's the system telling them, a classification of events. On another case, for example, the system may even adapt to altered working conditions in order to avoid the production line stop. Finally, you may consider also safety aspects because less failure and better maintenance also reduce the risks, making the system safer and simplifying in general compliance with standards and regulations.
So, Roberto, smart actuators may need to control and process a lot of data. How challenging is this for real-time systems?
Smart actuators embed a very advanced motor driver to support demanding algorithms and to achieve precise control and, in general, smooth operation. But they also must implement the functionalities of a sensor node, implementing a wide range of industrial sensors such as inclination, broadband vibration, audio, temperature, and so on and so forth. To design a smart actuator, you need a powerful data collection and analysis tool capable to manage a huge number of real-time data, combining the sensors I mentioned with motor control specific telemetries such as currents, voltages, feedback signals, and so on and so forth. So the tool must take care of synchronization and configuration of all those signals to be able to generate data sets that are useful to the design. Now, with this kind of architecture and tool setup, the intelligence you can design into the system is quite a high-level intelligence that can implement what we like to think of a digital twin of the motor, an actual virtual replica of the physical system that evolves in parallel to it thanks to all these sensing capabilities. Now, this opens the door to very advanced embedded AI solutions implementations. In smart actuators, the digital twin algorithms that you may implement have the capability to see, understand, and classify events happening in the physical world in and around the motor. The motor may be exposed to vibrations, for example, because of many factors that are external to it. For example, strong vibrations of a nearby machine, or maybe one of the screws fixing the motor to the ground is loose, or maybe there's a rare event like a earthquake or something like that. The transmission may become more difficult, so that more power must be used by the motor to actuate a belt while keeping the same rotational speed. Or in other case, the motor load may unexpectedly become unbalanced because of a broken ball bearing or some other disturbance factor at system level. In all these cases, you may want your digital twin to be capable to sense the events and interpret them and classify them.
So, Roberto, can sensing and actuation data be combined in predictive maintenance applications? And if so, what's the advantage here?
Let's consider, for example, a failure recognition and a predictive maintenance example. Like we see that a clear relation exists between early warning signs of potential failure and physical signals. We know that when some events happen and conditions start to change, they typically happen with very small changes. So small vibrations at very high frequency typically generate ultrasounds. Then, as the vibrations increase, they may be sensed as physical vibration by a MEMS vibrometer. And then other phenomena occur. So you may sense variation in the power consumption pattern, in the current, and as we get closer to the actual failure, other sensors can sense events such as noise, changes in temperature, smoke, and similar. So different sensors may give you different information concerning how close you are to the failure event. So we may consider the importance of having a broad range of sensors in your system. There's a specific importance in vibration sensors, both in terms of MEMS vibrations, so physical vibration of the system, and acoustic vibrations, so audio and ultrasound. The embedded sensor must cover from low frequencies to ultrasound vibrations to be capable to identify the signature of different failures, from mechanical misalignment to damaged bearings and all the other events that may be involved.
Roberto, what tool would you suggest that could be used by developers to capture such a variety of sensor data?
Our STWin.box is the third generation of a connected industrial sensor node. It is an all-in-one reference design for rapid development and field testing of industrial IoT solutions. It embeds ultra-low power MCU and a wide range of onboard sensors, 9 degrees of freedom motion sensing, wide bandwidth vibration, audio and ultrasound, very precise local temperature, and environmental monitoring. It also includes connectivity, wireless connectivity such as Wi-Fi, BLE, NFC, and why not also USB, so that it enables you to collect all this sensing data in an efficient way, also while doing field trials and during the actual experimentation on the field.
So, Ryan, what are some of the challenges for the drive portion of smart actuators?
I mean, I would say in my experience, some of the biggest challenges of designing these complex, sensing and controlling circuitry for actuators is the size constraints and power density of the system. We keep adding more and more features to these actuators and systems. The space we are allowed to use isn't growing as fast, right? It's mostly getting smaller or staying the same. And so, one way to combat this is with, a higher level of integration of the componentry that's on the board. The ST-Spin 32 family it's a really great way to reduce that number of components needed by combining analog and digital semiconductors in one package. As an example, the ST-Spin 32G4, it specifically integrates the STM32G431 microprocessor in the same package as the DC to DC switching regulator, a low voltage regulator, signal conditioning op amps, and a triple half bridge gate driver optimized for BLDC motors. And all that's in one package, right? So you can imagine that you're increasing the amount of silicon content in one package, which gives you more board space. And so you can see with a traditional discrete approach, you're using roughly 900 square millimeters of board space when you're adding in the passives of the capacitors, the inductors. With the ST-Spin integrated solution, it's only 324 square millimeters with all the passives. So it's a dramatic reduction in area required. And the ST-Spin 32G4 has enough memory and compute power to drive up to 2 brushless DC motors at the same time using some of the common drive algorithms such as 6-step and field-oriented control. And that can be done with or without sensors.
So, Ryan, talk to me about the tools for this solution.
That's a great question because having these ICs without tools to develop the application around or the system around, right, is you kind of need them both. There's both firmware development tools and hardware development tools available. Firmware development is straightforward with the ST-Spin 32G4. Anyone that's already familiar with the STM32 development tools, they'll feel right at home because the ST-Spin 32, it uses the same tool set that they've already been using. And even those that aren't familiar with the tools, that may be new to them, there's a vast knowledge base and training of materials that are available for people to pick up and learn, how to use the STM32 and the ST-Spin 32. And from a hardware standpoint, there's quite a few evaluation kits for ST-Spin as well, from general use kits for just learning how to use and spin a motor to high performance application kits that can control multiple brushless DC motors at the same time. And there's even one that's specifically built for smart actuators, the EVL Spin 32G4-ACT. It was made for this application. It was developed to interface perfectly with the ST-Win.box that Roberto mentioned earlier.
Just to jump on what Ryan was just saying, we have a full ecosystem around these hardware tools. And that's really just to let you use them as fully as possible. Part of this ecosystem in the development platform, all available on st.com, is having the ability to do high-speed data logging and sensors. So being able to understand the application from the point of view of the sensors that you want to be using at the end of the day around motor control and collect that data and be able to use that data afterwards. Just seeing things happen is great, but being able to then structure it and use it to develop solutions is really what we're aiming to empower developers and customers to do. So be it through storing data locally, sending it out to your laptop, or even through Bluetooth to a mobile application, really. And we have a suite of tools for that. We can use single sensors, and we have a lot of platforms around single sensors, but what we've seen is the use and real benefits of having combination of different sensors to really encompass large set of events, to be able to build the models that Roberto mentioned at the start and characterize the use case and take full advantage of the board that Ryan just presented. So be it current, voltage, control signals, vibration, and acoustic, which are pretty, maybe not standard, but at least a common combination of sensors available. And we have a suite of tools that will let you collect that data, visualize that data, and filter out and use that data as efficiently as possible.
Fantastic. Now, Louis, walk me through the flow here. How does a developer go from that data to a solution with machine learning?
From my point of view, on the data science point of thing, that's kind of the second step. The first step is that selecting the right platform, getting your sensors, and collecting that data. So you have that data capture whose goal is going to be to characterize your application, to understand what you're monitoring, the devices, the services you're monitoring from the point of view of the sensor you're using. What does it look like to your accelerometer, to your microphone, through voltage, and so on. And then specifically for these applications, we have a suite of tools. One of them is Nano Edge AI Studio. In that case, you can feed the data directly to Nano Edge AI Studio, which will generate your AI model for your end application. It will find within that set of time series data the best pre-processing as machine learning algorithm that will let you differentiate the states you want to differentiate between nominal states, nominal and abnormal states, and so on and so forth. And one of the real perks that we have is because you're using the tools and the ecosystem all the way through, deployment is absolutely seamless. The library you get at the end of this process, you can play with it, you can implement it on different platforms, but you also can just click and drag it into your project, in that case, on the STWin box.
So, Louis, I remember seeing Ryan mentioning the STM32G4 built inside the STSpin32. So, could that be used to run Edge AI?
That's a good question. And I know we talked about kind of a specific example, a specific set of use cases. I'm going to take just a quick step back with this one. The goal is obviously to have those tools run on the G4 inside the STSpin32. But the goal beyond that is to be able to run on any STM32. ST has been doing machine learning for more than a decade now, and it was mostly internal. And a couple of years back, there was demand from our users and customers, and we made those tools more and more available and packaged them to be able to be used on any STM32 out there. And that's still the goal. And it expanded beyond any STM32. The goal is to have machine learning, that kind of algorithmic solution, available on the most relevant platform for your use case. And that goes from the sensors, with some of the smart sensors that ST has, to the STM32s, be it microcontroller and microprocessors, be it general purpose ones, such as the STM32G4, or even ones with AI acceleration, such as the STM32N6, and have the tools for everyone to use them. So if you want to create your own model and just implement it, we have a tool that lets you import your own model. We don't see it, don't know about it. We just let you interface as easily as possible, as seamlessly as possible with the hardware and take advantage of the hardware. And we have other tools such as Nano Edge AI Studio or the Sensor Lab that let you create the algorithm from the data you collect without having to go out of the ecosystem, create something on another platform, import it, and fine-tune it yourself. So the goal really is to have that holistic, might not be the best word, but to have that full solution for developers and have that strong ecosystem around it, be it for the STM32G4 or any STM32.
So, Roberto, how would all of this combine into a practical example?
Well, let's look at three different and typical use cases. Each of them will show different role of the sensors and how the algorithm can detect different situations. Let's start from, for example, when there's an anomalous vibration imposed to the motor. Let's say that a vibration may be induced by some external factor, such as, for example, a nearby machine that is vibrating or some screw becomes loose and the motor starts having an erratic behavior with strange vibrations. Now, in this case, if we look at current and vibration signal as detected from the motor control algorithm, the current, and the vibration detected from an external vibrometer attached to the motor, we can see that this kind of vibration may not be visible at all in the phase current, whereas it is clearly visible in the vibrometer. So an algorithm receiving as input both signals, in this case, will just use the one from the vibrometer and will be able to clearly detect the event. In case number 2, we see a different thing happening. In this case, we have a motor belt that all of a sudden becomes harder to push. And so it is pulled by the system, in this case, to simulate an anomaly that is reflected on the load. The motor all of a sudden needs to push harder in order to keep the same rotational speed. Now, this is clearly visible in the phase current. So if the smart actuator has access to the current used within the algorithm of motor control, then it clearly sees that there's an increase in current, whereas probably, depending on how in a specific case the event happens, at the level of vibration, you may not see any spurious vibration at all in this case. So once again, an algorithm that has access to both this information can use, in this case, just the phase current and clearly detect the event that is happening and signal and classify accordingly the anomaly. On case number 3, we see another event that is basically, we may call it an unbalanced load, maybe caused, for example, by a damaged ball bearing or some similar event. In this case, because of the imbalance, we see some level of anomalous vibration both in the phase current and in the vibration sensor, in the external vibration MEMS sensor. Now, in this case, having the possibility to run an algorithm that uses both these signals, being the event visible in both sensors, clearly will lead the algorithm to improve its sensitivity and be able to detect the event in a better way. So overall, the 3 use cases that we have seen show how using a combination of one motor telemetry, the current in this case, and one external sensor, the vibrometer, again in this case, we have been capable to detect different events that are very different nature, that have very different signature, and leveraging of one or the other on or both the sensor, we have improved the level of intelligence and sensitivity of our, in this case, predictive maintenance detection algorithm.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me, Roberto.
Thank you, Amelia.
And thank you for joining me, Ryan.
No problem. It was great talking to you.
And thank you for joining me, Louis.
Thanks a lot, Amelia.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from STMicroelectronics. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.